Okay, so we're in 4.7 now, and we're looking at Cauchy-Euler equations. Now, Cauchy-Euler equations are linear differential equations that have a very, very specific form. We put very specific requirements on the coefficients of this type of linear equation. So let's start with the definition. This is an example of this is the general definition of a Cauchy-Euler equation. So notice what we have here is an nth order linear dE, and the coefficients on the terms of this dE are all monomials, a constant times x to the power, x to some power. But not only that, the power on this x is going to match the order of the derivative it's being multiplied to. So notice x to the nth power here, nth derivative of y here, n minus 1th power of x here, n minus 1th derivative of y here, and so on. Okay, it's a very, very strict requirement that those coefficients need to hold to, but if that's the case, then we're talking about what's called a Cauchy-Euler equation. Okay, now we're going to try and come up with a method for solving these, and our method is going to kind of resemble a lot of what we did back in 4.3. So there should be some kind of familiarity to the steps that we're taking here, but it's not exactly the same. So first of all, notice the g of x here implies that this equation might be non-homogeneous. G of x could equal 0 also, in which case we're talking about a homogeneous equation. But notice Cauchy-Euler equations can be either. They can be homogeneous or non-homogeneous. And in the non-homogeneous case, we know that we would have to begin by finding a complementary solution. So we would need to be looking at the associated homogeneous equation for this guy by setting that equal to 0. And so we're going to focus on that first, and to keep things manageable, we're going to focus our attention for the most part on second order equations. We'll look at higher order equations later, but for now, let's suppose that our goal is to solve a second order homogeneous Cauchy-Euler equation, which would look like this. This is the general form: ax squared y double prime, seeing the power matching the derivative. Bx y prime, first power on my x, first derivative of y, plus cy equals 0. Okay? Now, we're going to do kind of what we've done with other solution methods, which is we're going to make an educated guess as to what the solution might look like, throw it into our dE, and see what that tells us. So here's the thing. Since I have powers of x showing up in all of my terms here, I can think of this as x to the 0 power being in here. It kind of makes sense that, at least for the homogeneous case, that my solution might be also a power of x. So we're going to make that educated guess and then plug it in and see if it gets us anywhere useful. We're going to assume that our solution to this dE is of the form y equals x to the m, where m is some unknown constant that we're going to try and figure out. In order to use that in my dE up here, I need y prime and I need y double prime. So we evaluate those here. Y prime from the power rule is just mx to the m minus 1. Differentiate again to get y double prime. Now it's m minus 1, x to the m minus 2. We need to substitute those into our original dE, and that would give us something that looks like this. So in the square brackets, you're seeing where y double prime went. Here is where y prime went. X to the m, that's just y. Okay, equals 0. Now, it's at this stage that you kind of see why Cauchy-Euler equations are defined the way that they are. Because if you notice, we have 3 terms here, but when I multiply ax squared into this, for example, that x squared there, when multiplied to this x to the m minus 2 here, is just going to produce an x to the m. Okay. Similarly here, when this x is multiplied to this x to the m minus 1, it's going to just produce another x to the m. And I already have an x to the m here. So that tells me that all 3 of these terms will have a factor of x to the m after doing that multiplication. That means I can factor the x to the m out, giving me this, x to the mth power times this expression here, which is given entirely in terms of constants in that unknown value m. Okay? And that's equal to 0. So from algebra, you know your zero product property, you solve this by setting either of these factors equal to 0. But it's not actually useful for us to set x to the m equal to 0, because even though that has a solution, meaning, you know, if you plug an x in, or if you plug a 0 in for x here, then 0 to the mth power is equal to 0, provided m is not a negative number or 0. M would have to be positive for that to be true. That doesn't actually matter, because remember, we're talking about a solution to a differential equation here, meaning I'm not looking for specific values of x that would make this true. I'm looking for an identity. I need this equation to be true for all values of x, which clearly it's not. Okay, so that tells me that if this is going to be an identity, my only hope of that happening is if this expression, which is given entirely in terms of constants, is equal to 0. So I set that equal to 0. am times m minus 1 plus bm plus c equals 0. Or if I multiply the am and combine some like terms here, I can also write that as am squared plus b minus am plus c equals 0. Okay, so at this stage, this is starting to look like what we did in section 4.3, where we came up with an auxiliary equation, which also, in the case of a second order DE, was giving us a quadratic equation to solve. Back in 4.3, we broke that down into 3 cases, because any quadratic equation will have roots falling into one of 3 categories. We either have distinct real roots, we have repeated a single repeated real root, or we have complex conjugate roots. We're going to do the same thing here. Okay, so this is the quadratic equation that we're working with here, either this one or this one, depending on which form we prefer. Case 1, what happens if this quadratic equation has distinct real roots? Well, let's suppose that those roots are m1 and m2. That would mean, based on where that m came from, that x to the x to the m1 and x to the m2 are solutions to our DE. I would like for them to form a fundamental set of solutions so that I can use them to create a complementary solution. And we use our Wronskian to check that. Remember, here's my Wronskian. And when I perform the Wronskian on these 2 functions, I get this, m2 minus m1, x to the m1 plus m2. Now, because m2 and m1 are distinct real roots by assumption, then their difference is non-zero. So this will not be 0. Okay? Can this equal 0, x to the m1 plus m2? Well, yes, if x is equal to 0, then that would be true. And remember, for the Wronskian to establish linear independence, we need this thing to be non-zero for all values of x. We actually specified that back in 4.1. So does that mean that we do not have linear independence then? Well, only if we don't make an important restriction. We are going to take these functions, which are normally defined on all real numbers, but restrict them to the domain of only positive numbers. If we require x to be positive, x greater than 0, then this thing will always be non-zero, giving us linear independence, which means this would be our general solution, c1x to the m1 plus c2x to the m2. So for that reason, we will take this particular case, and we'll say our solution exists on this interval of validity, 0 to infinity. Okay, that's an important thing to keep in mind with these Cauchy-Euler equations. Our interval of validity only exists on these positive real numbers. Okay, let's take a look at case 2. In case 2, we have repeated real roots. I should actually probably just say repeated real root singular, because we're only going to get one real number out of this. So what we're going to do here, we look at our quadratic equation, and our solution in this case I'm going to say is m1. It's a repeated real root, which leads me to the following solution to our DE that we were talking about, y1 equals x to the m1. Okay, but remember, we need 2 solutions, and we need them to form a linearly independent set. Back in 4.2, we showed that we can get a second solution using reduction of order. So that's our next goal. We want to use reduction of order. In order to use reduction of order, however, the DE that we were starting with, which is this guy right here, has to have a leading coefficient of 1. That y double prime term has to have a coefficient of 1, which means I need to divide everything by ax squared. This is what that would look like if I did that. Okay? Now that we have done that, we can perform reduction of order. But there's another thing that's worth pointing out here, and we made use of this back in 4.3 as well. if we have a repeated real root, we know that the quadratic equation that we were solving to get that had to have a discriminant of 0. That means b squared minus 4ac would have to equal 0. And careful, because I'm using a, b, and c here, but really b, the b that we would be using in the quadratic equation is actually this b minus a here. We know that our discriminant of this quadratic equation has to equal 0. So trying to solve this thing using the quadratic equation would ultimately give us m1 equals this. You can verify this by applying the quadratic formula to this guy. I'm not going to do that here. I'll let you do that. m1 you can show very easily would equal negative b minus a over 2a. Okay? We would prefer to have this in a different form, however. So we're going to multiply both sides by negative 2 here. And actually, I made a little typo here. If I multiply both sides of this by negative 2, I still need to have an a down here. So I'll make sure and include that. Okay? All right. So now, what's next? What we want to do is use our reduction of order. So reduction of order is going to use, remember, p of x. P of x is the coefficient on your y prime term. It looks like b over ax here. So using that, we know that reduction of order requires the integral of p of x dx. So we're going to integrate that. That integral comes out to b over a natural log of x. Okay? And here you have your reduction of order formula, giving us that second solution. Okay? You can see where this ends up, b over a natural log of x. It's going to be the exponent that we use on e here. It's actually negative this. Remember, that's part of that formula. I'm going to let you actually look through the steps of this. It's just kind of talking through some kind of basic algebra and then calculus in this last step where we take an integral. But what reduction of order is going to generate for us is this second solution, x to the m1 times the natural log of x. That's going to be our second solution. So now we have this as our general solution for case 2. Y equals c1 x to the m1 plus c2 x to the m1 times the natural log of x. Okay? Now, again, I did say we're focusing on second order equations to start with. However, we will apply these things to higher order equations. And kind of similar to what we saw in section 4.3, if you're looking at a higher order Cauchy-Euler equation, a homogeneous one, it's possible to get these repeated real roots, m1 in this case, with a higher multiplicity than 2. You know, and when that happens, you can find kind of a more general set of solutions to use in your complementary solution. So all of these terms would show up as solutions to our DE if m1 had a multiplicity of k. Notice x to the m1, x to the m1 ln of x, which is what we got here. And then if we need more terms, we can start raising that ln of x, that natural log of x, to powers. Natural log of x squared, natural log of x cubed, all still being multiplied by x to the m1 out here. All the way up until we have x to the m1 natural log of x to the k minus 1 power. That gives us a total of k linearly independent terms, which will help us form that fundamental set of solutions. Okay? The last case that we need to look at is case 3, which is if that quadratic equation has complex conjugate roots. So suppose that's the case, and let's call those complex conjugate roots a plus or minus bi. It might actually be a bad idea that I used a and b here, since I already used a and b in my quadratic equation up here. I think your book uses alpha and beta, so that's kind of my bad. But just keep in mind that the a and b here are not the same a and b that are showing up there, okay? If these two complex conjugate roots of our quadratic equation turn up, then that means our general solution technically could be written this way. Y equals c1 x to the a plus bi plus c2 x to the a minus bi. But as was the case in section 4.3, we don't like having imaginary numbers floating around. So we want to do something to try and get rid of the imaginary numbers. And we're going to do some algebra here that's very similar to what we already saw back in 4.3. First of all, focus specifically on this term, x to the bi. This is the same thing as e to the natural log of x to the bi, since the e and the natural log would just cancel each other out anyways, bringing us back to this step. However, by writing it in this form, I can use that logarithm property that allows me to take the bi out to the front of this natural log. Now I'm going to do that, but I'm going to separate the b and the I. So I'm going to put the bi out here, and then I'm going to put the b and the natural log of x in parentheses, and then just move the I out here. I'm just using the commutative property of multiplication. My reason for doing that is because b natural log of x will be a real number, and so that's a real number times I, and that allows me to stick this thing into Euler's formula to represent it in terms of sines and cosines. So this thing, using Euler's formula, is equal to cosine of that number, b ln of x, right there, plus I sine of b ln of x, b natural log of x. If I plug a negative bi in up here, as we saw back in 4.3, the only thing that actually changes is this plus goes to a minus. Okay? Now, if I were to add these two equations together, add this top one to this bottom one, so that I get x to the bi plus x to the negative bi, we see cancellation in these two terms, and I get 2 cosine of b natural log of x from these two terms. Similarly, if I subtract them, we'll get a similar cancellation, but with the cosines this time, and I'm left with 2i sine of b natural log of x. Okay? Now, remember, in our general solution up here, right, this guy, I can pick any parameters that I want for C1 and C2. And so if I set C1 and C2 both equal to 1, then I get x to the power of a plus bi plus x to the power of a minus bi in my solution, which could also be written this way. I could take the x to the a as a factor and pull that out, and I'm left with x to the bi plus x to the negative bi in parentheses, which we found another way of representing that here. So that becomes 2x to the a cosine of b natural log of x. Okay? If I do something similar, but I choose different parameters, let's say if I set c1 equal to 1 and c2 equal to negative 1, then I get this. Y is going to simplify to x to the a times x to the bi minus x to the negative bi. And again, using the algebra we did on the previous page, I get this expression, 2i x to the a sine of b natural log of x. Now remember that constant there, that 2i, can be swapped out for any other constant, so what really matters is the rest of it, x to the a sine of b natural log of x, and on this page, x to the a cosine of b natural log of x right there. So those two things are going to represent solutions in their own right to our DE, and we're not going to show it here, but we could use the Wronskian to show that they do form a linearly independent set. So putting those together, we get that general solution. And this gives us the solution for case 3. Okay? I'm going to stop this video here. We're going to start looking at examples in the next video.